Okay. Professor Bai just mentioned that some of you not going to be here next week. So the notes you received ideally should be the order that I proceed. But because some of you are not going to be here next week, maybe 10 of you. So I'm going to use in a different order. That means sometimes the motivation and the idea naturally to bring the next idea might not be in the natural way. So I'm sorry for that, but I wanted to give you some idea of the recent development rather than straightforward. Otherwise, you won't be seeing any of that for those who are leaving. The handout that you have, maybe in the last page, there's a homework assignment. In that, the most written assignment is there by hand. Then there's a programming one. Let me pop the page. I create a page that contains a sample program that you can run. Start with test matrices, 3 of them. I didn't use all of them, but you can change the code a little bit to use one or the other. For the MATLAB function, I have 3 different kinds. The first one, 2, and is for the generalized eigenvalue problem with B positive definite. There's no chalk right here. B is positive definite. Of course, A, B are Hermitian. And then the last 2 category, number 3, so it mentions explicitly what is for so-called linear response eigenvalue problem. And then 4 is 3 and 4 for one kind with 1 for steepest descent and then a conjugate gradient. Number 5 is has one example for hyperbolic quadratic eigenvalue problem. And if you download them into one directory, they should be run, except the test metric may be changed a little bit in your code. Just change the path to that the which test problem can load. Then there are a few that auxiliary function that are going to be used by of them. So you're going to put them together. It should be run. It run on my laptop and it should run on yours. You can practice on them. My assignment basically that you take those code, you can modify them, run your own example, and particularly what I mentioned here, that you modify this code to create a so-called extended method, which we're going to talk about in the lecture. Okay, that's for the homework assignment. And one other thing I need to. I talked to Professor Peter Banner a little bit. He is, so this afternoon we're probably going to meet here we're going to run afternoon session in the parallel. And then we're going to meet here and see what happens after next. Okay. Some of you mentioned that wanted to give a talk, student talk on eigenvalue problems. And this week I'm teaching on Monday and Tuesday, and Thursday, Wednesday, Thursday, Friday, Dr. Sherry Lee going to teach. So if one of you going to give a talk, 10 to 15 minutes, is that 10 to 15 minutes? I think it will be better maybe tomorrow afternoon during the discussion session. So I'm going to hand out this piece of paper for those, if you want to give a talk on eigenvalue problem. Because the reason I said tomorrow, because again, some of you are going to be not going to be here next week. So let's list here, see how many people wanted to do that. All right, I'm going to pass through. Okay. Okay. Any questions before we proceed? All right. So, you know, there's a lot of eigenvalue problem exists for you know, how long? I don't know. Too long, maybe. So there are a lot of methods, a lot of books, and my theme in this talk is basically on Rayleigh quotient idea to solve a larger scale problem that you are not supposed to, the metrics typically going to be very large. You're not supposed to do any dense idea on it like QR algorithm. Using Rayleigh quotient that allow us to employ some of optimization technique. Okay. Now, it should be, so it should work. Why doesn't it work? Let me unplug it first. Okay. Huh? I tested it yesterday, it works. All right. I wonder why. Just give me a second. Huh. Oh, I wonder why. Anyway, the talk outline, starting with a couple of motivating examples. Of course, we have lots of examples for the eigenvalue problem. What I'm going to present two examples that attract a lot of attention in the recent, in the last many years. Starting with that, we talk about the basics of Hermitian eigenvalue problems. And again, Hermitian eigenvalue problems is one of the most important because a lot of, in physics and a lot of places that you do have Hermitian eigenvalue problems. And it has a lot of structures, lots of properties. So we're going to talk about basics of that. And after that, then we create a lot of the minimization principle, how do you minimize or maximize certain function. And that gives us to naturally need to talk about the basic optimization technique called Steepest descent, okay, or Steepest ascent. And after that is conjugate gradient. Then based on that, this is the natural order, but I'm going to mix it up as I mentioned before. That those optimization methods are made possible by the min-max principle. And then you naturally wonder how far we can go with the min-max principle, given the importance of this theoretical results in application. So I want to briefly mention a few slides on extending min-max principle for indefinite B, in this case A minus lambda B for B indefinite. Then move on to two applications, linear response eigenvalue problems. One of a problem that being used in electronic structure calculation. Usually the matrix is huge. Then move on to hyperbolic quadratic eigenvalue problems. Okay. Like I mentioned, I'm going to talk about two of them. The first one is called from electronic structure calculation, arrived from Courant-Fischer equation, being used. There's a survey paper by Joseph Sard and many others, and arguing that electronic calculation could be the next large-scale scientific computing and can compare with before was CFD computation. Then the next one is called trace ratio maximization problem. Is from the data mining. You all heard big data everywhere, and that also create a Hermitian eigenvalue problem. And more classical example in the chapter 10 of this book by Saad that republished by SIAM in 2011. So let's look at the Courant-Fischer equation. It's complicated as written here, but if you don't look, consider everything in bracket as one object, and it's an eigenvalue problem in continuous case. So operator times a function equal the eigenvalue times another times the same function. So it's a continuous eigenvalue problem. Then you look into the bracket, what you see that the bracket has Laplacian operator. Then you have the integral. What happened is a function called n of r. What is n of r? N of r is defined by the sum of the eigenfunction and times its conjugate. So it is. What's important here that the expression nr is depend on the eigenfunction. So looking at that the bracket itself, it depends on the eigenfunction. So that becomes a nonlinear eigenvalue problem. It's different from the eigenvalue problem we usually look at is that the matrix depend on the eigenvalue. This one, the operator depend on the eigenfunction. Okay, so how do we solve it? A typical way in physics would be so-called self-consistent field iteration, and the idea is basically very natural. You have a prediction of eigenfunction. You have a prediction of the eigenfunction to begin with, then substitute that into the everything in the bracket. By the way, this delta is functional variation, and it's like a derivative, but it's more complicated. Then you repeat the solving. Hopefully, that the procedure can converge. If it converge, then you solve it. It may not converge, but it hopefully converge. This has been the procedure that in the physics calculation do that. Usually it converge, but of course we can always create a problem. It doesn't. Now this is a continuous case. Every continuous case is going to be discretized, as we know. There are a lot of ways to do that. Finite difference, finite element, we all learned that in numerical analysis class. That's common. And then you have it's called plane wave, basically FFT style. You express a function into the cosine sine in that format. Then you use the wavenet idea. In any case, if you use any of the discretization, it's end up with a eigenvalue problem like that. H is a Hermitian matrix that depends on X. What is the X? X is basically eigenvectors. Each column is eigenvectors of. This S is a constant matrix. So this is an eigenvalue problem, and is the matrix depend on the eigenvectors, several eigenvectors. Okay. And how do we solve them? So similarly, self-consistent field iteration. You pick an initial approximation, x0, and you keep iterate. The idea seems simple. Two references I listed here is very much is written by mathematicians. At least one of them are mathematicians, so it's easier to be understood by us. And if you look at physical literature it's hard to make a sense of it. You spend more time on it. Okay, this is one of example being consuming a lot of supercomputing power in today's supercomputers. Okay, the next example is also more recent. It's from data mining. You have a set of many have a lot of data. Each data in terms of vector. So you have basically in mathematics you have lots of vectors. Each vector is a high dimension. The idea is how to separate those data into several categories. So it's classification basically. So how do we do that? You project the data to the smaller dimension. How do you project? You find a matrix, a tall, skinny matrix, and do an inner product, and the vector become smaller. So here comes a problem. Become in the math term will become a maximization of a ratio of two traces. It has meanings. In the numerator, the trace represents called in-between scatter. That's two category. So you have several classes. In-between class, we want to maximize. Then the denominator is within to minimize. Okay. How do we solve this maximization problem? Well, in the calculus, you know, when you have a function, you try to find the max or mean. How do you take a derivative? Here you do the same thing. You using taking a derivative and arrive so-called KKT equation. You can Google what's KKT mean. It stands for the first letter of three mathematicians. So you end up with again into an eigenvalue problem, and the big thing in the bracket is a matrix. So A minus something B. So together consider one matrix, and times V equal to V times this is a smaller matrix. V is a tall, skinny matrix. All right. So A is supposed to be big. So if you rewrite this the matrix in the bracket, square bracket as E of V, so you're basically solving the eigenvalue problem of E of V. This again is a eigenvalue problem depend on eigenvectors. So V is an eigenvector. The operator E of V depend on eigenvector. By the same token, that you can still solve it by self-consistent iteration, right? So those are the two examples that appear quite often in the literature recently. You can go online, Google them. Two reference for trace ratio. The first paper actually was selected as one of the best paper in SciMax in the last 3 years. Okay. Of course, then you have a lot of more eigenvalue problem in this book, Springer book on data mining. Entire chapter lists 7 to 8 eigenvalue problems arising from data mining. So it's one of the problems that happen you see everywhere. Okay. Now get back to the basic theory of the eigenvalue problem. A lot of them are, if you have taken either matrix theory class or numerical linear algebra, you would see most of them. Okay. So we're going to talk about the standard eigenvalue problem in the Hermitian, then talk about one application that to justify the common use called Rayleigh-Ritz procedure. And normally we don't think about that. In fact, it can be justified by the theory why we should do this. Okay. All right. The eigenvalue problem for the Hermitian case, you have a Hermitian matrix A equal to A H, and is n by n. Suppose n is big, but it doesn't matter here in terms of theory. So what we know about eigenvalue of a Hermitian matrix, all the eigenvalues are real, which means we can order them in order, either increasing or decreasing. Here we're going to do order increasingly. It doesn't matter, but if you order decreasing, it's still fine. But we're going to adopt this order. Then the eigenvector are orthogonal. We know that you have n orthogonal eigenvectors. Okay, this is a standard thing, and you can possibly think of there are lots of property for Hermitian eigenvalues. It's very elegant, most of the theory, and I'll list a few popular reference here. The first two references is more theoretical, called matrix analysis, written by first one by Bhatia, the second Hall Johnson. I presumably you know those two books. They contain pretty much everything you want to know, but probably too many. The next four is more numerical, contain minimum, not too many, minimum theory on the Hermitian eigenvalue problem that enough to do computation. I particularly want to mention Paulette's book, which has in the numerical analysis books, which has more than everybody else. Then into perturbation, how eigenvalue change if the metric perturbed. That's in Stewart and Swin's book. Okay. All right. So I want to mention one of a particular property called Courant-Fischer theorem. So you have again the Hermitian matrix eigenvalue order increasingly, Rayleigh quotient defined by A transpose conjugate transpose AX quadratic over A transpose X, and one of a particular min-max theorem due to Courant-Fischer is that you can characterize all the eigenvalue in min-max property. The last two is particularly familiar to everybody else. Okay, it's easier to prove. I list one of our homework problem, and for this last one. But let me just mention one of them, because both of them are similar. For this lambda I, what does it mean? This means that the first mean is mean over all subspace of dimension I. Then the second is a max. So once for each subspace dimension I, you max over all x. Okay, that gives you a rho x, and that turns out to be the eigenvalue lambda I. It's a beautiful theory and can be used not directly for computation, but it can be useful to help us to derive something. But the last two, this one, lambda 1, lambda n, lambda 1 as a mean rho x, lambda n max x, is quite useful. I mean, used in optimization method for solving eigenvalue problem. Because this one is more complicated. This one you just try to minimize rho x. Okay. Another usefulness is we can use to justify Rayleigh-Ritz approximation, and we'll talk about that later. Okay. The theorem sounds complicated. When you look at it, it seems complicated. The proof is not really complicated, but in the old days it can be complicated. One of the page in Paulette's book in I can't remember which chapter it mentioned that when he was taking class, he thought at the beginning this min-max theory was a deep mathematical theory. It's hard to learn, and then he said, and then once he realized it's basically about talking about two subspace, one of the dimension I, when the dimension adds together is bigger than n plus 1, then it has a common vector. This is basically the key point to prove the theorem. Okay. Okay. and we're not going to prove it here. Okay. The next is called trace. Well, before was just for one eigenvalue. Here's for some. Okay, that allow you to compute several eigenvalues together. This is the importance of this theorem. So the Hermitian matrix A, eigenvalue number 1 to number n, it says in the first equation said the first k eigenvalue together, first k smallest, equal to the mean of a trace x conjugate transpose ax. Here x has several columns subject to x h x equal identity. So k orthonormal eigenvectors you take in trace. Sorry, k orthonormal vectors. Okay. And the same is true for the largest eigenvalue. If you do max, you get the first k largest eigenvalue summed together, right? And the importance of this theorem is that we can for computing several eigenvalues together later. Okay. Again, this can do the same thing, justify the Rayleigh-Ritz procedure. Then also introduce in the previous slides we talked about Rayleigh quotient. Now, naturally, you can define so-called Rayleigh quotient matrix. Before was a scalar, now it's a matrix. So for x has several columns. So this capital X would be like that, right? And x h equal I k, and this would be a k by k matrix. So, all right. Cauchy interlacing inequality. So you have a matrix A. Usually, you look at textbook, when you look at Cauchy interlacing inequality, they talk about matrix, Hermitian matrix, and leading n-1 by n-1 principal submatrix. But that can be generalized to this. It's not too hard. So you have a matrix A. You have a x. N by k typically short, less than n, much less than n. Then kh equal identity. Then you can do a projection. This is a Rayleigh quotient matrix, and whose eigenvalue mu1 up to mu2. And it turns out the eigenvalue of this mu I is always in between of two eigenvalues of A, whose index differ by how much? A minus k. Okay. If k equal to a minus 1, which is normally you see, then would be each two eigenvalue of A has the eigenvalue of the projection matrices. And the theorem itself looks nothing in particular, but once you look at carefully, the theorem has tell you something. That is that in the numerical case, that because this mu I is in between, now it's between, could be either way, could be towards lambda I, could towards lambda j plus a minus k. So which way is close to? And how do you make them close to one to the other? So you can always pick x to somehow push mu I down. You can think of mu I as a ceiling has a floor. You can push it down. And once it pushes down, how far can you push it down? You do lambda j. That's when you're going to compute one of eigenvalue, right? Then you can, of course, you can push it up as well, right? Okay. Now, that's for ax equal to lambda x, b equal identity. What happens? B is not equal identity. B is a positive definite matrix. Turns out fairly, you can always do an equivalent transformation. So you have ax equal to lambda bx. What you can do is somehow rewrite, put b square root, this negative square root, that's a matrix function you just learned last week. So both sides, so you take a b negative half, b half to here put in front, so you get this equation there with x hat related to x by b square root. Okay, So basically, this you have a matrix AX, eigenvalue AX, eigenvalue from AX equal lambda BX. You have A hat X hat equal to lambda X hat. So the two eigenvalues are equivalent. They share the same eigenvalue, and the eigenvector is related by this relation, right? Okay. And because of this, and we know the eigenvalues are real, okay, then you using this relation discover that it has n linearly independent eigenvector satisfy this called B inner product. So B orthogonal, B orthonormal eigenvectors, the n B orthonormal eigenvectors, and naturally. You have for A hat, you have this Rayleigh quotient, but you substitute back in the Rayleigh quotient defined by this way. Before was B, if B is identity, this is get back to that. Now, this equivalent relation has an implication that once you have everything for AX equal to lambda X, you have you just translate. You just word by word translate. Nothing. Particularly difficult. So you would have same three theorem, all right? So you have min-max, Courant-Fischer min-max. That only thing is you're going to use a row X is a new row X. It's not the row X for B identity, right? Then for the trace mean, you have the same principle. Now, before was mean over, there's no B here, you stick B in. And if B is identity, you back to the old way. For Cauchy is that depend on whether you're going to have X edge BX identity or not, but you're going to put from one matrix pencil to another by project X from left and right, because the eigenvalue also real, then they satisfy that. So the same implication there. Okay. Any questions? Okay. Now, I consider these three principles are the most fundamental in terms of numerical computation. Of course, there are a more general principle that I didn't mention here for eigenvalue, Hermitian eigen, which is so-called Wieland theorem. In that, here you have it's a sum of select several consecutive eigenvalue, right, from number 1 number 2. Wieland theorem allows you to pick. So if you have order eigenvalue 1, 2, 3, 4 in that order, Wieland theorem allows you to pick, say, eigenvalue 1, 5, 9, and sum together. Then you have a min-max. It's more complicated. All right, let's do one application to justify Rayleigh-Ritz approximation. Why we are doing that? If we recall. When we try to compute the large-scale eigenvalue problem, what's all the most fundamental thing you need to do? To summarize, there are just two things for solving a large-scale eigenvalue problem. One is build a subspace, build a good subspace, the subspace that is close to the invariant subspace or eigenvectors, as close as possible. In fact, if the subspace you want to find is in the space you build, then you have the solution already. So that's the first thing. Then after, once you get a subspace, then you're going to find, how do I find the best subspace, best approximation using the information I have, right? The first one is, you heard a lot about Krylov subspace. That's one of the subspaces used. And you have other methods, for example, Jacobi-Davidson method. You build a subspace, you append one vector at a time. How do you build? So for the Rayleigh-Ritz approximation, is assume you already built a subspace. Then how do you find the best approximation? All right? So we're going to look at the second phase. So we have a subspace Y with dimension m, and we wanted to find the best approximation using this subspace Y. And how do we do? This is the procedure, standard procedure we do. We call Rayleigh-Ritz procedure. You take a Y as a basis matrix of the subspace Y, okay? And you simply do the projection. So the matrix, this pencil is m by m. You solve it because usually m is very small. You don't do a very large subspace projection. It's usually small. And when you have a small problem, you solve them. And then here's the approximation. You have an approximate eigenvalue, and we call it Ritz value, which is mu I, basically the eigenvalue. Then approximate eigenvectors, we call Ritz vectors, which is to take the basis Y times each eigenvector of the projector matrix, the so-called Rayleigh-Ritz. Then you're wondering, we do this all the time, but sometimes you may ask why it is possible, in what sense is it possible, okay? Let's look at a couple ways to justify. Now look at the Courant-Fischer. Courant-Fischer said lambda I is mean over all subspace of dimension I, right? Then you take a max. Now we, since we're knowing only the subspace Y, we don't have, basically we say we don't have the whole space. We only have the subspace Y. And because of the relation, it's naturally, given the subspace Y, so the clock is struck at 9:45, 8:45. So we're gonna run on 9 o'clock. So naturally replace the whole space by subspace Y, and using this approximation, and take a piece of paper, do a little calculation. You discover this mu I is the eigenvalue of that projection we just talked about. This is one way. The other way, using trace mean. So trace mean says the smallest k eigenvalue summed together equal the mean over x, HBX equal identity, and trace that. So what this suggests, what that means, it suggests, well, if we want to find the eigenvalue approximate to the first k eigenvalue, is we better minimize this trace such that the column space of the x is in the subspace Y. And again, you take a piece of paper, you do a little calculation, and that come up with the value, the minimum value of this trace turns out to be the eigenvalue of this pencil. Okay. Okay. I may go a little fast for this one. Let me explain a little more about why Rayleigh-Ritz. So there are two ideas to justify. By Courant-Fischer, so naturally replace lambda I by mu I defined this way, and then we claim mu I is the eigenvalue of this metric pencil. How do you do that? Well, we have this subspace Y has a basis Y, which is has m vectors, right? Linearly independent as a basis. Now each this subspace X is in Y. What does that mean? That means each vector, little vector X in subspace X can be written into Y times, let me call X tilde, right? Because X this little vector X is in the subspace Y, can be written there. Then we write, then become for all the X in this subspace X, this X tilde run through a subspace X tilde because the dimension of this little, this x, without tilde dimension I, this x tilde subspace dimension also must be I. Right. And therefore, if we write so mean x over the subspace curl x in subs y is become the mean over dimension of is x tilde subspace dimension I max over all little x tilde in the subspace curl x tilde rho x rho y x. Right? So it becomes this. Then you look at what is that? What's that? You can think of look at is Rayleigh quotient rho x equal to x f ax. Right? Then you plug in, best to plug in x equal to y x tilde, and that gives you now, then you look at, compare this with the min-max principle, then this number ui is the i's eigenvalue of the project one. So basically, that's how you derive that mu I is the eigenvalue. Mu I is the eigenvalue of that measure. Now, by the other one is very similar. So again, you write this now is capital X can be written y times another capital X tilde of k column. And plug in and best, then look at the mean press principle. Compared to that, you discover this average is become eigenvalue of this projection. So that's a big thing. So the next topic is this section is talking about steepest descent. On the convergence analysis part, there's a theorem proof that I'm going to leave out for today, maybe to next week. So we're going to plan to cover most of this section and then move on. For tomorrow, I'll move on to the linear response eigenvalue, new stuff. Best in natural order, we should go through this and then give us some idea, give us the idea how do we do frequency. All right, so we're looking at this problem. Ax minus now the bx. B is positive definite. And so we talk about the eigenvalue of real. We order them in the real line in increasing order. The eigenvectors of B orthogonal. So there's a complete set of B orthogonal eigenvectors. This is a Rayleigh quotient we talk about. Let's say we're interested in the first eigenpair. Then, of course. This is a simple assumption. You might be interested in other eigenpairs. How do you do that? We can talk about that later through so-called deflection. And this is for smallest. Then you may wonder, what about the largest eigenpairs? You multiply everything by negative and big to the smallest in a mathematical way. Of course, numerically, you replace everything by mean, replace every mean by max. It will go through. But theoretically, you can think that way. Tell you they're equivalent. If you can do one, you can do the other. All right. Now, steepest descent is a very ancient idea from Kepler's point of view. That it's nothing new. Let's look at, just to refresh our memory, steepest descent in general. So it's a general technique to minimize a function f of x. Now, why we call steepest descent direction, steepest descent method, is because the direction we're moving the function value. So how do you, the function, because this is a multivariable function, you look for a direction to move so that the function go decrease in the fastest fashion. So let's say we're at point x0 and we're moving toward along direction p. How fast we're moving? Okay, so you're taking derivative over t, and at t equal to 0, that's at this particular point, and we look at which direction we go, right? Then you end up with we want to minimize over p because we're looking for the direction where the function decreases the fastest. So the order calculus to show you that this derivative at t equals 0 is p transpose the gradient of f x0. Now, if we minimize over all p and of the unit vector, because where p is the direction, we make it a unit vector, then equal to negative the gradient norm squared. Gradient norm in the Euclidean norm, right? So when this is going to be equal, p turns out to be the opposite direction of the gradient. Okay, that's common sense. Okay, because this property that gives you a plan, the banana steepest descent, that is, you pick a f0 as the initial, and you keep at each xi, you're looking for the best t, because to move best t to as how far you go, and then you have the next xi approximation, and keep on so on and so forth. And you can there's a so you can draw a picture. What does this mean? It's basically through the contour. So so you have a function f(x). Suppose that you have an optimal point, the function value, the mean. Then you can draw a contour. For contour plot, right? This is I draw a very nice contour. It's not too flat. So suppose you have this point x, x0. We can start with any x0. Then this is the mean here, but at any particular point you do compute the steepest descent direction. This turns out this will be the gradient increase. This is the gradient direction, and the steepest descent says we're going to move in the opposite direction. See how far we can go to the function reduce the smallest, right? And usually we go to the so there's a contour right here, and when you go tangent, so at the beginning you go across all the contour, which means every time you cross the function value decrease, and each curve here the function value is the same, and until you tangent to a contour, and until you got this point. Then if you move any further, the function value increases because the contour will go like that, right? So this will be x1. And from that point, you get another you go another step, steep descent. You keep on moving, and every step you're going to make progress because you're going to reduce the value, and eventually, hopefully, you get smaller and right? That's the best idea of steep descent. Now, there's a little let's put a food for thought here. That what I put here before here is for real value function. The function real value and x is in the real value, the real vector as well. In the Hermitian eigenvalue, we just talked about a minus lambda bx. If A and B could be complex. A and B could be complex, the eigenvector could be complex. The rho x x is complex. So this is the real value function, but the variable x is complex. And the derivation here is this equation here, equation 2. If x is a complex vector, then this is not really, it's not right, actually. You have to do something else. So that's why I put it here, food for thought. This derivation 2 is not quite right for real value function of a complex variable, as we do here. Later we'll see a little bit about this, and you can think about that. So this is so-called the line search, because you're following this Steepest direction. It's a one line. So each step you find the best possible argument t, and then you move by ti, and then so each step you need to solve this so-called search, the line search. So whether this T is in C or R, which is complex or real, makes a difference. And whenever homework asks you to find an example that you will see a big, they're different. And usually, if the complex value function, real value function in complex variable x, you should use C in complex, okay, rather than R, because you can get more improvement. Okay. Now here you see a little serious difference between complex variable or not. So we're looking for lambda 1, which is a mean x over rho x. And the gradient, if you look at a lot of books, the gradient is calculated as equal to 2 over the correct form of b and times they happen to be a so-called residual. Rho x is the Rayleigh quotient. And one thing that with this important property that this residual R of x is orthogonal to x. So well, that's that can be easily verified. You can say ax minus, once you write it out, so let's write out a rho x. Okay, if you do an inner product, that gets you 0 because you see the second term x transpose, conjugate transpose bx and cancel and become cancellation, becomes 0. So that's orthogonality is natural once you written everything out. So how do you find the gradient? One way you can the gradient is, what is the gradient? It's basically the linear term. You look at the linear term. So let's say we change move x to x plus q, and q is a tiny magnitude vector. You change a little bit and look for the linear term. So you plug in, you expand them out, you drop out the quadratic term. So we're going to only look at the linear term. The quadratic term, we'll drop it out. See the quadratic q transpose AQ, I drop it out because of the quadratic term. So then numerator stays sum, denominator is x bx. Well, how do you get this? Let me write one out. So you write out that equal to xb okay, and this is the denominator. When this denominator, this one you're going to put if I put inverse here, and then you have inverse here, inverse there. The first inverse here is up to right there. The inverse of 1 plus, remember q is tiny, so 1 plus small number, drop the high order term equal to 1 minus that, right? So. Right, then you drop a high order term. That's why you see 1 minus this thing right there, and you combine and you do it. Now it's a simple algebraic manipulation, and become rho x, the constant term, then the linear term. Linear term, you look at the numerator, it will be q transpose rx plus rx transpose q, when this is going to be the smallest or maximum in a negative way. So this happened to be q equal to q, right. So to become twice over x transpose bx rx. Q in that direction give you the steepest, give you the most negative value. All right. Okay. Now we talked about steepest descent for the general function. Now is for this for our function rho of x. So we know the gradient is parallel to this, and because of the way we do optimization here, this only direction matters. The direction multiplied by a number only going to change the step length ti. So doesn't. So instead of so we're not going to divide by that. We'll just take the residual. So you start with the x0. You do that until convergence, and then each step you compute the optimal argument, arginf. Here I want to mention that if you look at the old book, other papers, they probably see argmin. I put an arginf because this t might not exist in a sense. T could be infinity. Okay, you may argue infinity is a number, but normally we don't think that way. So t could be infinity, and when t is infinity, which means this Rx is a 1. So if t infinity, you're not writing that way. You would simply say xi plus 1 equal to R of xi. Okay. But this simple scheme, okay, very simple. There are two things you need to look at, need to solve before actually put into the working code. The major one it would be how do you solve this the one-step minimization and so-called line search. The second one that is look at until convergence. So when to stop, right? You're going to decide. You don't want to run forever. You're going to stop somewhere when you need it. Okay. Well, let's look at line search first. Okay. what we're looking at if T in C, the reason behind C, but we're talking about Hermitian matrix. If your example is a real matrix, real, A and B are symmetric, you could say C equal to R or T equal T in R. You don't have to put into C, make it more complicated. In the real cases, you can prove that T in R is the same as T in C. They give you same value. So if this is, one can prove that this is equal to the row is a minimization over all the linear combination of X and P. Here just you can think of the combination constant in X is 1. Here's here's in both. And then here's the absolute value of C squared plus zeta squared bigger than 0. In fact, you can make it equal to 1 as well. The reason is the Rayleigh quotient matrix is homogeneous. If you look at this function, this is homogeneous, which means if you multiply x by any constant that's not 0, it doesn't change. So you can prove this is true. Again, I put it into the homework. You can look at that. So then you look at the last one. This is xp is fixed. So and then you write out this become a smaller eigenvalue of 2 by 2 pencil. Okay, right, where x equal to x and p. Suppose x and p are linearly independent. How do you see that? You can see that by looking at the following. You write cx times theta p, that can be written of xp is a linear combination of that. If I call this, let's just simplify, call this y, then you look at the Rayleigh quotient, the row of y equal to y transpose ay, y transpose by. And then you plug in, again, I call this big X, it become, call this one vector z, become little z transpose x transpose ax. And so that's why is you minimize this, then give you the smaller eigenvalue of this 2 by 2 matrix pencil. Okay, so end up that's why I say this value is the smaller eigenvalue of this 2 by 2. Assume x and p are linearly independent. If x and p are independent, what do you see? If x and p are independent, the value doesn't change, right? So if you look at x and p are dependent, then new improvement. Okay, here's the thing. Say if x p dependent. If x p dependent, let's say p equal to this either way. Let's say p equal to a alpha x. All right. It could be other way around. X equal to alpha p. Then you look at row x plus tp. That equal to row x plus alpha x equal to row 1 plus alpha x. Now, we just mentioned this Rayleigh quotient function is homogeneous of order 1 with respect to x. So if we multiply x by a constant, scalar constant, doesn't change. So in this case, you don't improve anything. you just stay the same. We hope it doesn't happen that way. But then you look at steep descent method doesn't happen if you're using the direction p equal to rho x. It doesn't happen. So if p equal to rx, that x and p always linearly independent, unless you are at a solution. That's because if x transpose r orthogonal, right? So if x is not zero, assume if r is not zero, they are orthogonal. X and r must be linearly independent. Okay, so that doesn't happen. But it can, if you happen to have a p linear independent, it doesn't. It won't move anything. Okay, so so suppose this is 2 by 2 pencil. Let's say we can solve by hand, or it's easy. So you can compute the mu with eigenvector v. Then rho. Then the solution to rho xv equal to mu, and xv you can write nu1 x plus nu2 p. Then the best possible argument would be there are two choices. If nu1 is not zero, you can take nu1 out, become nu1 times x plus nu2 over nu1p. So there you got the optimal argument t. Or if nu1 equal to 0, what nu1 equals 0, what that means? That the best vector is p, which t is equal infinity. All right. So okay. So in a way you can solve this linear search like this. All right. In the real case, when A is real matrix, real symmetric, B is a real symmetric, and I mentioned that T, you can pick T in R, and in T equal R, this becomes a single variable function. You try to find mean. How do you find the mean of a single variable function? You take derivative equal to 0, right? But if t equal to in C, then you cannot do that. If t in R, you can take a derivative, and this happened to be a Rayleigh quotient function. Plug in the derivative. Still, I think it's still a little bit more complicated. You take a derivative, become a quadratic equation. In the numerator, you set a quadratic equation equals 0. You have two roots, and then you're going to pick which one. After a careful analysis, you would know which one is which. So, but this is probably the easy one. Okay. Now, moments ago, I mentioned a picture that if intuitively, if you start from here, you stop at the next position, and the next gradient should be perpendicular to the direction of moving. So what this means that you start with at x, you do a line search along the gradient along. Well, it doesn't have to this gradient, but when you have a p direction, this will be true too. So if you this is gradient direction, but if you move many particular p, it's also true. You're going to stop at a certain point where the gradient here is going to be perpendicular to the direction. What this means is so the p going to be perpendicular. The residual direction is the gradient direction the next point. So the proof is not too difficult. So there are two choices as we look at the previous slides. The solution, either the vector, the next point of y is p, or is x plus t optimal p. Okay, there are two possible case. So in the case if y is p, if y equal p, then you have p transpose rp. That's equal to 0 we talked about before. So I erased it. So we talked about before, one of the property is X transpose Rx equal to 0. Okay, we just mentioned before, if this and this are the same, it's always 0. So y equal P the same. So if y not equal to P, that means T is not infinity. So we're going to do rho y. Then rho y, this is how defined, and because we can always shift this. Okay, x plus TP, we can always write the following: x plus TP. You can always x plus T optimal P plus T minus T optimal P. And you call this a little another variable s, and this would be y. So it can be written as mean rho y s in C, and then this is optimal in S thing, S equal to 0, right? Because this is the optimal eigenvalue. In the whole thing, this will be y plus SP going to be optimal when S equals 0. So you look at S is tiny, rho y plus SP, linear expansion, as we talk about, to become rho y plus 2 over y transpose by, then the real part of this inner product, okay? Overall possible, now S is in every possible real number, small, around 0. And so for this to be minimized, the linear term has to go to 0 for all S, for every possible S real number. That means that has to be equal to 0. So you get that point. And the other inequality, the X transpose Ry equal to 0 can be prove in a similar way. I'm going to just skip that. So what it means that when you do a line search so X from X and Y, the residual equals 0, and P direction also equal to 0. All right, so that takes care of a line search problem, a simple problem. It's not too difficult. The next one, when are you going to stop, right? For stopping, this is we all do that you look at the residual. If the residual Rf equal to 0, the ideal case, if Rx equals 0, you have the solution. Now in practice, you don't have 0, as we all know it. It can only be tiny. So the normalized residual, this is called normalized residual, is more than a certain tolerance. You pick a tolerance. The reason you have to normalize is because if you normalize, this will be the magnitude gets out. So usually put a relative residual as small as 10 to the minus 16, which is a double precision, single precision 10 to the minus 7. But normally you don't go that far. You make it a little bit bigger, like 10 to the minus 14 or maybe 12 or something. So this will be the stopping criteria. Then you look at what's the implication of stopping criteria. One can prove that if this stopping criteria is satisfied, then rho x, this is scalar, that's a vector, is an exact eigenpair of perturbed, and now backward error analysis up here. So this pair is an exact eigenpair of A plus E minus lambda B. Now the question is how big E is. Well, let's assume the X is univector, because the eigenvector you can always normalize by any number. So we let normalize one. It turns out this E, the smaller E that can make this exact eigenpair would be the same as a residual norm. So that's good. So if the residual norm is small, that means the number you report is the exact eigenpair of a nearby one. This is for 2 norm. For Frobenius norm, you just put a square root 2 there. This E is a Hermitian matrix. so-called looking everything backwards. And there are more in this kind of results that can be useful to interpret the accuracy of a computer number in this now widely cited book called Templates for Solution of Algebraic Eigenvalue Problems. Again, look chapter 5 on that. Okay. Any questions? Yeah.
And at one point you mentioned using the residual as the search direction. Isn't that quite dangerous because of cancellation?
Residual, yeah. Well, when the residual, yes, when the residual is contaminated by the rounding error, you don't have to do your approximation is good enough already. Yeah. That's true. You look at residual, there's a lot of cancellation in computer residual. But when the residual would be so much contaminated that give you nothing information at all, then this tolerance will be satisfied already. Yeah. Okay, that's the framework of steep descent, simple enough. So you take a initial, you always provide an initial. And normally in the sample code that I provide on the webpage, usually you take a random vector. That's when I don't know anything, you just put a random. Then we're trying to compute the first eigenpair, all right? Giving a tolerance, like I mentioned that in the double precision, maybe 10 to the minus 12 or 14. In practice, you don't need that kind of accuracy, but 10 to the minus 12 or 14 is a good number. So you normalize the initial approximation, and then compute the residual, which is a gradient direction. Then you do the iterate. If the stopping criteria is satisfied, you stop. Otherwise, you keep doing that. All right. Every step, there's a 2x2 eigenvalue problem you have to solve. Here is a residual. As I mentioned moments ago, that if x and p, the search direction, are linearly dependent, you won't get anything. But with the gradient direction r, they're always linearly independent, unless r equal to 0. In that case, you're happy, and we're happy. So you compute the new approximation and then return back. Okay, all right. So I put it here. This in line 6 is the rank is always 2 unless the residual equals 0. Okay. Now let's look. You can test the code and then download it afterwards today and see how it works. And it is a kind of a knowledge that for steep descent method, there are pros and cons. Pros is it's very easy to implement, right? You look at the framework, maybe take a little time to just get your code running. And it's very little memory requirement. Every time you keep two long vectors, and keep doing that. Every good thing that comes with bad things typically go together. So there's a bad thing, a cons, that is slow convergence. This is the common in the optimization area, that steep descent can be very slow convergence. That happens when I draw a contour here, that when the contour is very flat, maybe I should. When the contour is very flat, usually you take a lot of steps. So if you're somewhere there, that's not a good place. you go and you go every step. You don't go very far and towards the center. So in the zigzag, every step you and take a lot of steps to do the solution. This is well known when the contour is becoming very flat, and could be flatter than this. They can draw. Now this is typical for mathematicians and maybe engineering too, that you identify a problem, then you propose a solution, right? So how do we rescue that to make it better? There are two solutions. One is you look at the line search. So every step is a dimension 2 line search. The line search is in the two-dimensional space. That can we get if we minimize in the subset dimension 2? Then one idea is we can make a space larger. You minimize over a larger space. In the extreme case, you minimize over the entire space. Then you have the solution, which of course is not practical, but is an extreme situation. So one of the ideas is to expand the subspace. The other is modify the search direction. So here that gradient direction, see you have the final point right here. The gradient direction going this way. This is not point to the direction. The ideal case somehow, if you know magically that along this direction to a search, you would be searched to the right place. Of course, we don't know that either. And then the one idea would be, well, instead of going this gradient direction, you maybe go through the other direction, and could be possibly better, right? That's the conjugate gradient direction. Yes.
So when the contours are really flat, does it say anything about eigenvalues? Are they like close to each other?
Yeah. It's well, not necessarily. If it's a very flat, what that means you have eigenvalue close. No, you have eigenvalue have various magnitude, right? If you look at a symmetrical eigenvalue problem, in the canonical decomposition is an ellipse, right? Some axis long, some short. If all eigenvalues are equal, you have a sphere, which would be ideal. You just go to the center no matter where it started. So you have lots of eigenvalues. You have a magnitude vary widely. You have a lot of huge and small in terms of magnitude, right?
But if all eigenvalues are equal, how do you find the smallest one?
If all eigenvalues are equal, every eigenvalue is smallest.
Yes.
Right. So that will be ideal. Any place start, you get to the right point.
It still converges to one unique eigenvalue.
Yeah. It converges at one step. I guess if the contour is a sphere, so if you look at the contour is a sphere, no matter where you go to the center, one step, right? That's ideal. But that's two extreme cases. Normally don't have that. Okay. So these are two ideas we're going to do. The first idea, expand space. The second idea, there are two ways: conjugate direction using conjugate gradient, or using so-called preconditioner. So preconditioner means that the gradient direction is somehow point to the direction that far from the optimal solution. You modify it by some so-called preconditioning. Okay, that's two ideas to do. Okay. extended method basically doing is that you look at the residual. You look at the residual. The search space is X, Rx, right? Then the search space turns out to be, you look at is a Krylov subspace of order 2 of this matrix A minus rho X B. And then naturally that I can make a space better using high order Krylov subspace. Okay. Now, right, so you can make a mth order. So naturally, just the idea just to modify the method by the step C. It used to be the Krylov subspace for order 2. You make it order m. Of course, what m to use there's no easy solution. Okay. All right. Okay, everything else is the same. One comment here: if B equal identity, is A minus rho I. The Krylov subspace is basically the same as Lanczos subspace. So this has become a restarted Lanczos. Okay. Okay. Then then you have to compute the basis. This one can be done on Lanczos. Okay. I want to go further a little bit to skip this and come back later in the next week. But I want to show you the two theorem, a convergence theorem, but not a proof. Then we're going to stop for today. And tomorrow I wanted to move on to the linear response eigenvalue problem. Okay, let's see what follows. One theorem says for this steep descent or extended steep descent, it's always converge. The reason it's always converge because we always minimize things. The number rho is always go down, okay, but it cannot go below number 1 because the quotient interlacing inequality. So this rho is go down, but never go and at least number 1. So go down with the lower bound below, they're going to converge. That's for sure. And another thing that the residual also goes to 0. Okay. All right. I don't want to go to the we'll go to proof next week, but want to show another convergence theorem with a rate of convergence, because that provide a future preconditioning explanation. So for that theorem, I'll introduce a so-called Chebyshev polynomial, which when you take a numerical analysis class, you almost always you will learn this Chebyshev polynomial. It's used quite often either in algorithm or in convergence analysis because of so many extreme property. So here's a jth Chebyshev polynomial of first kind. If for t is between -1 and 1, it can be defined as cosine j times arc cosine t. Bigger than 1, you can have this expression that don't look like a polynomial, but you can create a recursive relation to see they are polynomial. So for example, t0, j equals 0, this is 1. J equals 1 is t, and then afterwards you have this 3-term recursive relation. Okay, this is one of the beauty. The other is that so-called that for Chebyshev polynomial, for any polynomial, this is shows that the Chebyshev polynomial between -1 and 1 is always bounded by 1, but once out of that, it goes very fast. It's faster than any polynomial. In what sense? You look at all polynomials of degree j, no bigger than j. Those polynomials taking value no bigger than 1 between -1 and 1, then after the interval, outside interval, the Chebyshev polynomial is biggest. Okay, it means it increase faster than any other polynomial. If they all bounded between -1 and 1 in the interval. You can quantify this by computing Chebyshev polynomial. So you look at t bigger than 0, then 1 plus t over 1 minus, this is outside -1. Let's see. One of them, well, is outside -1 and 1. Okay, for any t that's not 1. And the value can be evaluated equal to this. What's the delta t equal to square root t plus 1? Again, this number will be bigger than 1 for t bigger than 0 and raised to jth power. So the bigger the t, no, it's not the bigger. The closer the t to 1, the bigger the delta t, and the faster the value is. Now, when t close to 1, what does that mean? If t close to 1, that means this is away from 1 further and further. Okay. All right. And this is a sample plot, a few for t from 0, 1 up to 5. And the first one is just a value 1. The second one is a straight line. The dotted line is not very clear blue, green, is plotted from -1, 1. And as you see, this is this band is getting squeezed in the middle. You don't see much, but those outside -1, 1, the function just go well, still polynomially, but it's go very fast. Okay, it's how do we use this Chebyshev polynomial in practical estimation or convergence? So this is one scenario of using Chebyshev polynomial. You look at the interval alpha, beta, and gamma is not in. You seek a polynomial, excuse me, less than m degree, and so p gamma equal to 1, and the polynomial we think alpha, beta is minimized. This is one scenario that normally we get used for gamma. So you take a value at 1 here, and this part is as small as possible. Okay. How do we do that? The idea is usually we map this to interval -1 and 1. Okay. You create a transformation, map alpha, beta to -1 and 1. And then in that, you can use the Chebyshev polynomial. And when you map this to -1 and 1, gamma is, so alpha map to -1, for example, beta to 1, and gamma going to map to a point right here, a t gamma. Okay, at that point, it's outside -1, and the Chebyshev polynomial value is very, very big. So you have you can verify there are two mapping. This mapping from alpha beta to t, and it happened to be -1, 1. Then t gamma, if gamma less than alpha, this is negative value here, if gamma here. If gamma is right here, because gamma is outside, then t gamma is positive right there. So the optimal polynomial would be Chebyshev polynomial of degree m, and you have to divide by the value at t gamma, so that this p at p of gamma equal to 1. And the maximum value within alpha beta that we want to minimize turns out to be 1 over this. You can calculate that, all right? Then you look at this eta. Look at gamma. So if gamma is alpha less than alpha here, the eta equal to the distance between alpha and gamma distance over the distance between gamma and beta. All right. So this number is going to be less than 1. Then you look at how close than 1. If alpha and beta close, the closer alpha beta is, the closer eta going to be. Eta going to be 1, and if in that case, then the function gets bigger and bigger. So this is one of the situations that typically Chebyshev polynomial get used. Okay. Okay, I want to show this theorem, and then we're going to be off. This theorem is talk about the extended method in the subspace search. We use m-dimensional subspace. Is in a book by Golub and Ye. So suppose lambda 1 is a simple eigenvalue. We look at simple first. Lambda 1 less than lambda 2. Let's say we're close to in between lambda 1 and lambda 2. This omega I are the eigenvalue of A minus rho LB. So this as a single matrix, not as a metric pencil. V1 is the eigenvalue, or eigenvector. Then the rho L plus 1 minus lambda 1 less than equal to the previous difference times epsilon m squared, and times, this is a high order term. See, this is a 2/3 of the rho I minus lambda 1. So when it's close enough, this is high order term. So it's basically the first two terms, the convergence depends on mu m. What is mu m? Mu m is the best polynomial that taking value omega, so omega 1 right here, omega 2, omega m. So this f, the possible optimal is taking one value here and take it as small as possible. The max value between omega 2 and omega n. So if this number is small, so every iteration you go, this error is reduced by square of that number. Okay. Let's look at some special case. So, of course, this number we don't know. Let's look at special case. If m equal to 2, so if m equal to 2, what's the optimal polynomial? That turns out to be a linear polynomial, because f is m equal to f is linear. F is linear at this point, that this number equal to 1. And how the optimal polynomial going to be? And if you draw a lot of picture, you will discover this is going to be the one that's passing through the middle of omega 2 omega n. Okay, and this then the maximum value is right here. Okay, so you can calculate that. For m equal to, it's easy. You can know the optimal value. It turns out to be omega 2 minus omega 1, omega n minus omega 1. So it's a difference between this over that. Now, then you look at the extreme case, omega 2 equal to omega n. So this becomes a single point. It becomes a single point. And then if it becomes single point, is you draw a picture, omega 1 here, omega 2 equal to omega n. This value equal to 1, you can always draw a line, go through that, and then, you know, the epsilon m equal to 0 right away. If it is equal to 0 right away, then you have the fastest convergence. Okay. In general, epsilon m we don't know. You can use. I just mentioned the one application of Chebyshev polynomial. You take this one, you make this interval as small as possible. That's how you construct them. So I think I'll stop here.